All right, I'm going to move quickly here. If I make some mistakes, my apologies. I'll do my best to keep it clean. There's a lot of little pieces of work to do here. All right, so this says that we've got some KOH solution and we are titrating it with nitric acid. So we know we've got a strong base and a strong acid, and we're starting with base. So KOH is just OH minus. And nitric acid, HNO3, that's just H plus. So we are starting with OH minus. Not off to a great start here. Let me rearrange myself. Okay. All right, we're starting with OH minus and H plus, and that's going to give us water. I'm not going to put equilibrium here because these are both strong acid, strong base. This pretty much goes to completion. The backward reactions probably has an extremely small K value. All right, so let's see what we got. We've got our OH minus. We've got 25 milliliters. I'm going to immediately convert that to liters. So 0.025 liters. And we are at a 0.1 molar. I'm not going to put the extra zeros. And for our H plus here, just going to clean this up a tiny bit. For our H plus here, our HNO3, we're at 0.1 molar. It doesn't give us volumes. Actually, it gives us our volumes over here. Okay, so what would be the pH if I added this much H plus? That's what it's asking me here. So if I have, I'm going to immediately convert this to liters, 0.0249 liters. And we have a 0.1 moles per liter solution, moles per 1 liter. That cancels out liters. That leaves me with moles. And this is going to give us, wow, what happened there? This is supposed to say 0.0249 liters times, okay. If we multiply that out, that's going to give us 0.00249 moles of H plus. So that's the number that's going to go right here. 0.00249 moles of H plus. Well, how many moles of OH minus do I have? Well, let's calculate this out. 0.025 liters times 0.1 is going to give me 0.0025 moles of OH minus. Okay, so when we're doing strong acid, strong base, this is just essentially a limiting reactant problem, right? One of these is going to be used up first. And as you can see, since they're in a 1-to-1 ratio, this one is going to be used up first. So what we'll do is we will subtract this out. All of this gets used up. And again, because it's in a 1-to-1 ratio, the amount of the OH that gets used up is going to be 0.00249 moles. So let's subtract that out. And we're going to get 0.00001 mole of OH minus left over. That's how much is left over. So if I need the pH, I need either the H plus concentration or the OH minus concentration. So let's see if we can get the concentration of this one. We need volume, right? We've got moles. We need volume. What is my volume? Well, I have my original 0.025 liters and my new 0.0249 liters right there. We add those together. We're going to get 0.0499 liters. So I've got moles, I've got liters. Let's divide that out. We're going to get 0.00001 moles of OH over 0.0499 liters. And that is going to give us, let's calculate it out. 2.0 times 10 to the negative 4. So this is our OH concentration. .00 times 10 to the negative 4. So let's immediately take the negative log of that, and that's going to give us our POH. I never round until the end. I'm going to take the negative log of the number that's in my calculator. And I'm going to get 3.698. And that's what I'm going to write down here. 3.698. But that's my POH. So I'm going to do 14 minus 3. Wow, that's gross. 698. And that is going to get me 14 minus that number there is 10.3. 10.3. So my answer for this one is pH equals 10.3. Boom, boom. I would suggest doing this work on another paper if you're going to be as messy as I am. Do the work on another paper. Staple that paper to this. I need to see your work. If you don't do the work, you're not going to get any credit for this, all right? All right, so 10.3 here is my answer. Let me clean this up and we'll do the next one. This next one's very easy. The answer is pH equals 7. How do I know? Because I have the same molarities in these solutions and the same volume. That means I also have the same number of moles of each, right? 25 milliliters here and 25 milliliters here. So equal amounts of H plus and OH minus. They're going to react to create water. And so if I needed to justify this, pH is equal to 7 because the concentration of H plus is equal to the concentration of OH minus. Therefore, this is a neutral solution of 7, at least if it's at 25 degrees. We're going to assume that it is. All right, this next one. What if I had 25.1 milliliters of my acid here? So let's calculate this out. 0.0251 liters times 0.0, no, that's not correct. 0.1 molarity is going to give me 0.00251 moles of H plus. So now we can see again, this is just a limiting reactant problem. However, this time OH minus is going to be consumed completely. So OH minus is my limiting reactant. So I'm going to subtract that out. That goes away. And if I subtract it out from this 0.0025, I'm left with 0.00001 moles of H plus. Very, very small amount. So we need concentration. Let's figure out our volume. Our volume is 0.025 liters. That's what we got from our original solution. And then this added solution is 0.0251 liters, which is going to give us 0.0501 liters. Cool. We'll divide that out. We'll get our concentration. Our concentration is 0.00001 moles divided by 0.0501 liters. And that's going to give us gotta count those zeros. 1.99 times 10 to the negative 4, pretty much 2 again, right? So this will equal my H plus concentration. This equals 1.99 times 10 to the negative 4. And I'm going to take the negative log of that to give me negative log of that number there. It gives me 3.69. We can round that to 3.7. And that is my pH of this one. pH is equal to 3.7. Part of this is to show you that the difference of 0.1 milliliter can make a humongous difference in pH. Notice 0.1 milliliter difference here takes us from 10.3 to neutral. 10.3 is pretty basic. And then 0.1 milliliter on the other side of excess acid takes us all the way down to 3.7. Not burn your face off acid, but definitely something you don't want to get in your eye. Oh boy, this is the hard one. It's going to take you a little while to do all these, but once you get the hang of it, your life will be easier. So here we got a 20 milliliter sample of 0.2 molar something. We can see that COOH, that it's a carboxylic acid, and so we see we've got an acid. Who cares? It's HA, right? That's what matters. That's what it is. It's HA. So this is our HA. And it's titrated with sodium hydroxide. Luckily, they're both the same concentration. That'll make our life easier. It says, calculate the pH after following volumes of base have been added. Excuse me, and then it gives us our Ka. So at first it says, okay, 0 milliliters of base has been added. That is just a weak acid calculation. So we've got HA dissociates into H plus and A minus, and it gives us our Ka here. So we could do our whole ice table thing or whatever, or we could just do our H plus concentration is going to be equal to the square root of Ka times our acid concentration, which is 0.2 molar. And then we're going to take the negative log of that. So we could actually rewrite this calculation even just a little bit. We can say, let's go. I'll write it backward to give myself some room. So negative log. So pH is equal to the negative log of that. This was that simple weak acid, weak base calculation that I showed you before. Let's calculate that out real quick. All right, so I've set us up here. We'll get that. Oops, I messed it up. What did I do? I put so negative log. Oops, 1.3 times 10 to the negative fifth. All right, and we're going to get 2.79. So our pH on this one equals 2.79. All right, so this is how this works. This first one with 0 milliliters, this is a simple weak acid calculation. We can see that at some point, look, I got 20 milliliters of 0.2 molar. When I get 20 milliliters of this, that's my equivalence point. So this one's my equivalence point. This one's special. But until we get there, these three are gonna be Henderson-Hasselbalch. Because, how do we know? Because the Henderson-Hasselbalch equation is when we have a buffer system. How do we know we have a buffer system? If we have a buffer system if we have acid and conjugate base in the same system, at least a substantial amount of either one. I'm sorry, a substantial amount of both. And that's what's going to happen when we start adding this base. So these are really easy. And then after we get to the equivalence point, we'll talk about that. Then these down here, these are just same as before, limiting reactant problems, strong base. That's it. Really simple. So here we've got our weak acid base equation. Now I would hope that you wouldn't just follow along with me, that you would try these on your own. Here we'll have limiting reactant problems similar to what we did. And I would hope you would try these on your own before this is equivalence point, and I will show us exactly what to do here. It's a special one. So let's do this. Okay, so we've got our HA. I'm just going to clear this up, because these three are going to use a very similar formula. We've got our acid, we're going to titrate it with NaOH, which for us is just OH minus. And this is an equilibrium. We are going to get water, which we don't care about at all. And we're going to get some conjugate base of our weak acid. Okay, so at first we've got 0.02 liters of 0.2 molar HA. Let's calculate moles right here. Let's calculate moles. So that's going to give us, I believe it's going to be 0.004. Let me double check just in case. 0.2 times 0.02 gives us 0.004. So this is 0.004 moles of acid in solution. So here, let's calculate how many moles of OH are going to be added. So if I got 0.01 liters times my sodium hydroxide concentration is 0.2 molar, this is going to give me 0.002 moles. Okay, so if I've got 0.002 moles here, these are going to react in a 1-to-1 ratio because this base is so strong, it's going to pull off all of these hydrogens. This is somewhat of a limiting reactant problem. We know that this is all going to be used up, and we know that this is going to be used up in a 1-to-1 ratio with OH. So we can subtract that out, and what is left will be 0.002 moles. The extra little step we have to do, though, is how much A minus is going to be created. Well, again, a 1-to-1 ratio, that's just stoichiometry. If it's in a 1-to-1 ratio, then it's going to be 0.002 moles of A minus. If we have moles, molarity, percentage, anything like that of A minus and HA, we can use the Henderson-Hasselbalch equation. So let's do the pH is equal to the pKa, so negative log of Ka, 1.3, times 10 to the negative fifth, plus the log of the ratio of A minus to HA, which is 0.002 to 0.002. Let me put that in my calculator real quick. All right, there's our calculator. So if we put that into our calculator, and then obviously 0.002 over 0.002 is just 1. So if you put the number 1 in there, that's fine. We hit enter, and we're going to get 4.88. That is the pH here at 10 milliliters. pH equals 4.88. And we're going to do something similar with all three of these. So let's calculate out the 15 milliliters. I'm going to erase much of this. I'll put you on pause so you don't have to see it. Okay, I think this is clear enough because we're still starting with the same amount of the acid. So let's see how much OH is being added at this point. So let's calculate 0.015 liters times 0.2. And I think that's going to give me 0.003 moles of OH. We can kind of see what's going to happen here. 0.003 moles. Sorry, it's real ugly. Not much better. So, again, kind of here, a little bit of a limiting reactant problem. This is all going to be used up, but this is also how much A minus is going to be created. So that goes away. 0.003 of this is going to be neutralized, so 0.001 moles will be left over. So now I have my ratio. I left my Henderson-Hasselbalch equation here because I don't really need to change much of this. I just need to change the ratio. So my ratio is now products over reactants, 3-to-1. If you literally put the number 3 here, that would work too. And then we can, cheat a little bit in our calculator. We can just go back up and replace those numbers. So we replace this number with 0.003 and this one with 0.001. And we're going to get 5.36. All right, last one. 19.9 milliliters. I feel like I gotta let you do this one on your own. It's the exact same thing that we just did 2 times. You need to calculate a new OH number, like an amount, and then you need to figure out the new ratio for the last Henderson-Hasselbalch equation. Don't forget, it's only with the Henderson-Hasselbalch equation that you can use moles or molarity or percentage, whatever the actual ratio is. You just need a ratio. For these other ones, you need concentration. So don't forget that here we're going to have to divide by the total volume. I'm going to clean this up so we can move on to the next part. Okay, so this is where things flip over. We are going to reach our equivalence point. We know we're going to reach our equivalence point because it's at this point where we're adding 20 milliliters of a zero point 0.2 molar base solution to 20 milliliters of a zero point 0.2 molar acid solution. They're going to completely neutralize. So that I know that I got 0.2 liters here and 0.2 molar, and that's 0.004 moles. And so these are both going to be in a perfect ratio to cancel out completely. What we can't forget is that this also creates 0.004 moles, not molarity, moles of our conjugate acid, whatever our 8 acid is here. So what do we do now? Well, if in our solution this acid is gone and this base is neutralized, then all we have is water and conjugate base. Well, now this is a weak base problem. So we got to rewrite our equation. We've got A minus plus water gives us HA plus OH minus. Look, it's the same exact equation. We just wrote it backward. But that indicates to us now that we're running a different reaction. So what do we need? We need to get A minus concentration. We know we have 0.004 moles. And we know how much volume we've had. We've had 20 milliliters of our original sample and 20 milliliters of our new sample. So that gives us 0.04 liters. Gosh, I just cannot write tonight. Sorry. Right, 20 milliliters plus 20 milliliters gives us 40 milliliters, which is 0.04 liters, right? So let's find our concentration. We're going to take 0.004 moles. We're going to divide by 0.04 liters, and I don't remember what that is. It's going to be 0.004 divided by 0.04. That's going to give us 0.1. So we have a concentration of 0.1 molarity. Now we have our concentration. That's what we needed because this has become a weak acid base equation. How do we do a weak acid base equation? We take the negative log, negative log of the square root, and this time we need Kb times the concentration of our base. What is Kb? Well, we have Ka, so to get Kb, we have to do 1 times 10 to the negative 14th divided by Ka, which is 1.3, times 10 to the negative 5th. And I think it was some spicy number that we got. What was it? So 1 times 10 to the negative 14th divided by 1.3 times 10 to the negative 5th. I think I did that wrong. Nope. Never mind. That's our number. Man, I remember it being something different just a second ago. Nope, I double checked it. That is our KB right there. 7.69 times 10 to the negative 10. So let's put all this into our equation right here. Let me turn off my calculator. So we're going to do negative log of the square root of what he just said, 7.69 times 10 to the negative 10 times my A minus concentration we just figured out was 0.1. And we're going to get 5.05. Don't forget though, this is our POH because that was KB. So my POH is equal to 5.05, 5.06. So my pH is equal to 14 minus 5.06, which is going to be 8.94. So my pH on this one, oh man, I made a big mess here, didn't I? My pH on this one is 8.94. Good job, us. Okay, these other problems here, these two problems here are almost exactly the same as the problems we did up here. Because once you get past the equivalence point, all you're really doing is adding excess base. Excess base is just strong base, so make sure you account for milliliters, add the milliliters together, get the new concentrations, and do the same exact thing that we did up here. That's it. It's like this problem all over again. Okay, I'm not going to do all of these. This video is running long. I'm going to pick number 5 and number 6. I'm not going to lie, I'm going into number 5 a little bit blind. I remember number 6. I remember how to do number 6, but I don't remember number 5. So we're going to work through this together a little bit. I'm going to zoom in just a little bit more. Okay. So we have a weak monoprotic acid, just means one hydrogen, and we want to determine the Ka. So we dissolve 2 to the negative third moles of acid in 100 milliliters of water, and we titrate it. After 20 milliliters of strong base, 0.05 molar, the pH is 6. What is the Ka of the acid? My first instinct is to automatically set up my acid plus base equation. We're going to get water and conjugate base. All right, and then we've got, what's that going to be? 0.002 moles in 0.1 liters. If we divide that, we should get, I'll double check, 0.02 molarity. So let's see. Right, 0.02 molarity. So we got our 3 numbers there. And then we're saying we put in 0.02 liters of OH, and that was 0.05 molarity. I'm going to clean that up just a tiny bit. It was 0.05 molar. My pH is equal to 6. Given pH, I'm wanting to do the Henderson-Hasselbalch equation because it's asking me for the Ka. Yeah, I think that's what's going to happen. Okay, so we got a pH of 6. So our pH is equal to our pKa plus the log of the ratio of A minus to HA. So I can get the ratio here. Okay, I see. All right, so we've got, this is what we're going to do. We're going to do 0.002 moles of our acid. Let's find the moles here. That's 0.02 times 0.05, and I think that's going to give us 0.001. 0.02 times 0.05 gives us 0.001, so 0.001 moles of OH. And this becomes the same problem that we had done before. If this is how much OH I have, then this is my limiting reactant. This all gets used up. It creates an equal amount of A minus 0.001, and it uses up that much acid, 0.001. So we're left with 0.001 moles here. And 0.001 moles here. We could divide by the volume, but it's not going to make a difference. Our ratio is our ratio. We're going to get 0.001 over 0.001. Now you could just put it into your calculator like this and figure it out. But the log of 1, because this is 0.001 over 0.001 is 1, right? The log of 1 is 0. So if you have equal amounts on top and bottom, that just goes away. So my pKa is 6. Remember, P means negative log. If I need to do the anti-log, I have to remember that instead of just doing 10 to the 6, I have to do 10 to the negative 6 because I did negative log. So negative anti-log has a negative right there, right? And that's just going to equal 1 times 10 to the negative 6. That's my Ka. Okay, number 6. This one is fun. I think it's similar to the last one we just did. But it is multi-part, so it's slightly more complicated in a couple different questions. What is the Ka of this? Okay, so we've got some monoprotic acid. 1.55 grams is dissolved in 15 milliliters, and it's titrated to 75% completion. This is a little bit tricky. Be very careful when you see this. I'll show you why. With 90.23 milliliters of 0.1 molar sodium hydroxide solution, and then it gives us the pH, and then it gives us the full titration curves below, which is this right here. But that doesn't really give us any new information at the moment. So it says let's find our Ka. We're gonna do something very similar to what we did before. We're gonna say our Ka, we can find it by taking the pH. The pH is 1.96 is equal to our pKa plus the log of the ratio. So let's find the ratio. But actually that ratio is really easy to find right now because they told us this percentage. Now this I don't know exactly what it is. I think if you don't have a lot of practice with it, this will trip up a lot of people, this percentage. If it is 75% titrated, so let's look. I'm starting out with X amount of this plus OH, and we're going to get cheese and rice. We're going to get water and A minus. So if 75%, let's pretend this, let's make our lives easy and just say we started with 1. So minus 0.75, I'm left over here with 0.25, and I've created 0.75. I'm not putting numbers because this is the percentages of whatever we started with. So the ratio will be 0.75 over 0.25. And this is the thing that people will get backward or get wrong. If it's 75% completed, that's how much A minus we have. And in fact, if you really do get this, like if you really see it, then that percentage could make your life easier. We can just say, well, we've got 75 to 25, otherwise known as 3, log of 3, right? If you get that. If not, just put these numbers in. It'll work itself out. So let's figure this out. The log of 75 over 25. Let's do that real quick. The log of is equal to 0.477. So let's do 1.96 is equal to pKa plus 0.4771212, whatever it is. So let's get rid of this by subtracting it from this side and subtracting it from this side. I'm going to use a number in my calculator. 1.96 minus that number there. It's going to give me 1.4828. So my pKa is 1.4828. Therefore, my Ka is equal to 10 raised to the negative 1.48. Again, we use negative because p is negative log. When we do the anti-log, we got to put a negative here instead. If I put that into my calculator, I'm going to get an answer of 0.0331. Actually, I got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. I've got 4 significant figures everywhere. So I'm going to put 4 significant figures. I could also write this as 3.311 times 10 to the negative 2. That's my Ka value there. All right, I'm not a big fan of this one because this just seems more like a math problem. Part B seems more like a math problem than anything else. So I'm going to do part B. I'm going to do it up here so we can see it and we can see the original problem at the same time. This is super easy if you understand how we can go backward and forward with percentages. So this is if 1.55 grams of the unknown acid were titrated, then what is the molar mass of the acid? I say super easy. I just mean this is the only way that it becomes clear. If you can go backward and forward with percentages. So what we're saying is we've got a certain amount of this acid. We've got 1.55 grams in solution. And we're adding X amount of moles of base to it to completely neutralize it. If 90.23 milliliters of sodium hydroxide neutralizes 75% of it, then how much would neutralize 100%? And so if you think about it, I don't know how much 100% is. It's X times 75%. We can change that to a decimal. Is equal to 90 point, whoops, 90.23 milliliters. And so here now it's really clear 100% would be to divide both sides by 0.75. And we're going to get 120.31 milliliters. So what I'm saying here is it would take 120 milliliters of base, 120.31 milliliters of base to completely neutralize everything here. So then let's just figure out, well, how many moles is that? And then we can figure out how many moles this is, right? So let's do that. So first let's convert to liters. So I'm going to move this decimal over. Move this decimal over 3 places. And so it's 0.12031 liters times the molarity of my base, which is 0.1. And so I'm going to get, add another 0 in there. So that gives me 0.012030603 moles of hydroxide. This is how much hydroxide, how many moles of hydroxide it would take to completely neutralize this acid here. So since they're in a 1-to-1 ratio, that means that that is how much acid, this is how many moles of acid that I started with, right? And I started with that many moles of acid, and that was 1.55 grams. If you remember, if you let your units dictate your math, if we're looking for the molar mass of something, what is the molar mass? Molar mass is grams per mole, literally telling us divide the grams by the moles. So let's do that. We're going to do 1.55 grams divided by 0.01203. Again, I'm using the number in my calculator, and we're going to get 128.84 grams per mole. And actually, it looks like we should round that to 4 significant figures, so 128.8 grams per mole. Again, this is the answer for part B. A little bit more of a math problem. I guess it's a bit of a stoichiometry problem as well. All right, let's clean some of this up. And this next part ain't no joke. The numbers just get a little weird. Okay, so we're going to keep all of this stuff in mind up here. Let's write down, before we move, our total volume, because it says down here, the next question is, the next question is, what would the pH be at the equivalence point? The equivalence point is, we just calculated that this is the amount of OH minus that would have been used to titrate to the equivalence point, 100%. So that's our volume. Our concentration of OH minus is 0.1 molar. And our original solution was 50 milliliters. And I think that's all we need to solve it. We also need our Ka, which we calculated earlier, to be I believe we calculated it to be 0.0331. I rounded a little when we did that, and I got a slightly different answer than the key. As long as it's close enough, it's good. Okay, I'm going to leave those numbers there. Let's work this out. Okay, so it says, what would the equivalence, the pH be at the equivalence point? So we are assuming that all of this is gone and all of this is gone too. We're at the exact point where they are at perfect ratios. If we multiply this out, we turn this into liters. Let's turn this into liters. So that's 0.12031 liters of sodium hydroxide and 0.05 liters of our original solution. We'll add that together. We're going to get 0.17031 liters. This is our total volume. Okay, our Ka is 0.0031. Well, if this is gone and this is gone, this becomes the same kind of problem that we did before, where now we only have conjugate base. So now we're talking about a weak base problem. And so what we need to do is we need to get OH minus concentration by taking the square root of Kb times the concentration of A minus. So at this point, what we need to know is how much A minus was created. Well, if I had, let me find a good spot. Let's do it right here. If I had 0.1 molar NaOH and I put in 0.12031 liters, then this will tell me how many moles of NaOH I put in there, which would be 0.01231 moles. This is also the amount of A minus that was created. So this is our amount of OH and our amount of A minus. So now we need the concentration of A minus. How do we do that? We're going to divide this by our liters. 0.17031 liters. and that's going to give us our concentration. Let me do that in my calculator real quick. 0.012031 divided by 1. And that's going to give us, so A minus concentration is equal to 0.0706, etc., etc. KB equals 1 to the negative 14 divided by Ka, and that's going to give us 3.02 times 10 to the negative 13. Okay, so here is A minus concentration. Here is Kb. We'll put those into this calculation, and what we should get, what I got, was OH concentration. Whoops. Oh, I didn't do that one. Okay. What I'm going to get then is square root of that times that. Okay. This gives us 1.46 times 10 to the negative 7. We'll take the negative log of that. And we're going to get 6.83. This is my POH. So I'm going to do 14 minus 6.83. That's going to get me my pH, which is equal to 7.16 approximately. So this is my pH at the equivalence point. What would be a good indicator for that? Let's find an indicator that has an endpoint. That has a... What did I do with my indicators? Are they up high? What would be a good indicator for that? 7.16. Right here. 7.16. Right here. Bromothiamol blue would be a good indicator for that one. Okay, these ones you can do on your own. If you need help on the other ones, let me know. This video has gone way too long. That's it. Thanks.